Today we're going to be talking about polynomials and end behavior of their graphs. There's a couple steps that we have to go through for this process. The first is we're going to make sure we have a polynomial and classify it, and then we'll be able to use its classification to understand the end behavior of the graphs. Here's an example of a polynomial, basically just a bunch of terms where each one has a different x with a different exponent, right? So we've got x to the 7th, x to the 5th, x to the 4th, x squared. We could have any combination of these. You could have, some x to the thirds. You could have some just x's. You could have, this has 5 terms. You could have 3 terms. You could have 7 terms, 6 terms. There's a bunch of different types of polynomials we could have. But what's important is that each of the terms has an x, or maybe it's just a number, and the x's have different exponents. That's going to define our polynomial, when then we'll be able to understand what's going on about it. So, first off, we need to make sure we have a polynomial and we can understand its classification. Let's take a look at that. So, with this example, we have a polynomial. There's a bunch of different terms. There's a bunch of different x's with exponents. We've got a number here. But it's not in the order we need. So the first thing we need to do is put it into standard form. And the way we're going to put it into standard form is we're going to shift all the x's towards the left in descending exponential order. That means put the largest exponent term first, and then the next largest exponent term next, and so on and so forth. If there's ever a place where you have 2 of the same exponent terms, this is a negative x and a negative 3x, those have the same exponents, you combine them into a single term. So this is going to be negative x, negative 3x, that's negative 4x total. Again, the first step we need to do is to shift things around so that the exponents start at their greatest value and decrease as we go to the right. So, again, the highest exponent term is this x to the 5th. We bring it towards the front. We have a positive x to the 5th, so we have a positive x to the 5th. The next highest, 2, 4, and 1, 4. Our next highest exponent is this 4th degree. So we'll put this term here, negative 2x to the 4th, next in line. 5, 4, we don't have any third powers. We do have a second power, so that's comes next. 7x squared. It's positive, so we add it. Now here's what I was talking about. After x squared comes x. We have this x and this x. We combine them into negative 4x and put that here. It's negative 4x, so we subtract it. And finally, we have one number, 2, and we tack that on at the end. So the first step of this process is recognizing we have a polynomial and putting it into standard form where the exponents of our terms decrease from left to right. This allows us to understand what's going on here. And by understand means we get to classify it. So here's where we classify it. Classifying our polynomial just means looking at the very first term's exponent. This number is 5. This is the leading term of our polynomial, now that it's in standard form. So our polynomial is of the 5th degree. This is a 5th degree polynomial. Now that we know the degree of the polynomial, we can understand the end behavior of the graph of this polynomial. Let's look at that. We have 2 options for our leading term's exponent. Either that leading term's exponent is going to be even, or that leading term's exponent is going to be odd. There's no other option, either even or odd. And that determines a bit of what the graph looks like. To understand what we're talking about, when we say end behavior, is that that means when x is very negative, the value you're plugging in for x is like negative 100 million, or very positive, 100 million in the positive direction. Those are where the ends of the graphs are, and so that's what we mean by end behavior. What happens when x is very negative, and what happens when x is very positive. So let's compare what happens when we plug in a large negative value or a large positive value here in our even exponent x terms, or when we plug in for our odd exponent terms. So if we plug in very large negative value in any of our even terms, we're going to end up with a positive value. For example, if we plug negative 10,000 into x squared, we get a negative times a negative. That's a positive value. If we do it into x fourth, that just adds on 2 more negative factors, and that's going to continue to give us a positive value. And if we add on 2 more negative factors, x to the 6th, we get still a positive result. So no matter what this number is, as long as it's even, if we plug in a negative value, it's going to give us a positive result. That means that all the way to the left, it's going to be way up high. So our end behavior looks like this. The graph increases as we go in that direction to the left. Notice what happens if we put in a positive value. Same thing. Positive times positive times positive times positive is positive. So if we're plugging in values all the way to the right at 10,000 or larger in the positive into an even exponent term, an even exponent leading term, the value is going to increase and stay positive. So the end behavior over there looks like this. Remember, again, we're going to be graphing these polynomials, or at least understanding what their graphs look like. And for an even exponent leading term, the graph is going to increase whether your x value is negative or whether your x value is positive. Let's see how it's different for the odd exponent leading terms. This means we're only going to have 1 or 3 or 5 factors. So look at what happens when we plug in negative 10,000 here. If we plug in 1 negative 10,000, that's a negative value. So when we plug in a negative value, we get a negative value. If we plug in 3 negative values, we still get a negative value because we have an odd number of x factors that are negative. So negative times negative times negative is a negative. If we plug in 5, we'll still get negative. So for our odd exponent leading terms, when you plug in a negative value, you get a negative result. That's why it's different than the even exponents where we plug in negative values and get a positive result. So that's the difference. And what that means is, when we plug in a negative value here, we're looking at way towards the left, but we're getting a negative result. That's way down. So the end behavior of the graph decreases as we move towards the left. If we move towards the right, we're putting in positive values here, and we're going to get a positive result. So similarly to our end behavior of our even exponent terms, the end result to the right is positive. So that's how the even or the odd changes the result of the end behavior of our graphs of polynomials. There's one more thing to take into consideration. We'll look at that now. So in the previous example of end behavior for even exponent leading terms and odd exponent leading terms, we were looking at those where the leading term was positive x squared. positive x to the fifth. And it doesn't even matter if there's a coefficient. 7x to the sixth, 15x to the third. What we need to look at now is what if those values are negative? For example, a negative x squared or a negative x cubed. The negative is affecting this term after we do the cubing. This negative affects this term after we raise it to the fifth. Same is true over here. This negative affects this term after we raise the value to the fourth degree. So anytime we multiply by a negative, and that's basically what's going on here, the values are going to switch, or the sign of the value is going to switch. So, for example, when we plug in that negative 10,000 here 2 times, if this was positive, we would have gotten a positive. But now that we're multiplying it by a single negative factor, we're going to get a negative result. Again, this negative doesn't end up getting squared. It's not part of that process. It's just tacked on out front. So we get the 2 that we would have gotten from the x squared, the 2 factors of negative 10,000, and then we get another negative factor, not a 10,000, just the negative part, and that gives us a negative result. The same will be true for any of these even exponent terms. If we have 6 negative 10,000s, that would give us a positive result, except for now we're giving it a single negative factor in addition, and that gives us an odd number of negative factors and creates a negative result. And when we plug in a positive value here, we would normally get a positive, but now we're multiplying it by that single negative factor, so we're getting a negative result. What this means is when we plug in a very negative value, right, like negative 10,000, we would get negative 10,000 times negative 10,000, that's positive, times a negative, that's negative, that's here. Our end behavior for this graph to the left decreases. But the same is true when we go increasing to the positive, we also decrease. So even exponent leading terms have end behavior that are in the same direction. When we look at a positive leading term, they both increase, they both went up. When we look at a negative leading term, they both decrease, they both go down. So even is either both up or both down. For odd, remember we had 1 down and 1 up when it was positive. It's going to split when we look at the negative term. If we plug in negative 10,000 3 times, we would normally get a negative, but now we're including one more negative factor, and so this result is positive. This tells us that as we look to the left, our end behavior of an odd exponent leading term that's negative is going to be increasing. And as we switch that and go positive, positive times a positive times a positive times a negative is negative. And that means that when we plug in a positive value and an odd exponent leading term that's negative, we get a negative value, which is decreasing and going down. So our odd exponent leading terms are doing 2 things, either starting down and going up, or starting up and going down. They're always ending in opposite directions. Again, even exponents are both up or both down. Odd exponents are 1 down, 1 up, or 1 up, 1 down. So that's end behavior, that's the whole thing. It's a long process, but the breakdown is fairly simple. So we'll do the breakdown next, and you'll go step by step and really come to understand how this all fits together.